So, hello everybody and welcome. This is the next episode of our seminar for mathematical physics. And it's my great pleasure I can introduce Štěpán Hudeček, who was so nice to promise that he could repeat his talk once again, even though it's 10 p.m. in Queensland, I guess. So we are really happy about your approach. And what's even nicer, Štěpán brings for us Poisson equation on homogeneous spheres. So everybody is surely looking forward to your talk. I think I don't have to introduce who Štěpán is. He's a PhD candidate in University of Queensland, and his work revolves around G structures and generalized geometry as such. So if you're ready, Štěpán.
Yeah. So thank you very much, Iri, for the introduction. So I guess first thing first, can you hear me all right? Yeah. I guess you can. Right. So yeah, thank you very much for the invitation to speak. And yeah, let's get straight into it. Maybe I guess before I start, like if you can't read anything or don't understand anything, really just please ask. I love questions. I think it's much more fun that way. All right. So let me start really slowly by recalling what is a holonomy and what is actually a G2 group and G2 structure on a manifold. All right. So let's start with the holonomy. Right. So given a Riemannian manifold, let's call it MG. We have a parallel transport, right? So the picture you should have in mind, right? This is a sphere. You have a vector. You can parallel transport it. Let's say here, and parallel transport it over there, and then parallel transport it back, and you end up with a different vector, right? So essentially, your parallel transport along closed loops gives you a transformation on your tangent space. Maybe if you're more categorically minded, you can think of it in the following picture, a commutative diagram, right? You have your fundamental group of the manifold, and this in general maps to, let's say, diffeomorphisms of your fiber, of your tangent fiber, and you factor out by some homotopy. This is, of course, your monodromy representation for your tangent bundle. And above here, you have the whole loop space at point P. This surjects down here. And the holonomy map is essentially left. Holonomy is associated to a connection, in this case, Levi-Civita connection. So holonomy map is essentially a left of your monodromy to, let's call it, diffeomorphisms of your fiber. But holonomy is actually much nicer because it actually lands in linear transformations of your fiber. And even more, because we are on a Riemannian manifold, it lands in the orthogonal transformation of your fiber, right? So this is a commutative diagram, tells you what a holonomy is, right? And I hope that's clear, that everyone remembers what a holonomy is. And now you immediately have a question, well, what are all possible holonomies for your group? And why do we even care about holonomy? Well, we care about holonomy because it essentially tells us what are the global parallel structures on our manifold, right? For example, having holonomy of our manifold to be inside UN, this means that we are actually on a Kähler manifold. So understanding the holonomy really tells us the global structure of our manifold. So what are all possible holonomies? Well, for that, let me introduce, the full list of possible holonomies was given by Berger in the 1950s, but there was this one important lemma, which I want to mention, So this lemma was given a couple years after Berger by Solomon. Right. So the lemma goes as follows. Given a Riemannian manifold, right, that's simply connected, right? You can always assume that because you just pass to the universal cover, and also a manifold that's irreducible. By that I mean the holonomy does not split as a product of two groups. Again, if it is equal to a product of two groups, you can apply the round decomposition theorem and get their manifold is actually product, and then you can essentially you can reduce to the irreducible components. Okay. So what does the lemma say? Well, the lemma says if your holonomy group is not transitive on spheres, then M is a symmetric space. Right? And that's kind of remarkable. So first of all, if it's actually not transitive on spheres, your holonomy group, we are on a symmetric space, and we know how holonomy groups of symmetric spaces look like. We actually know how all of the symmetric spaces look like because they were classified by Cartan, I believe, in 1920s. So this is essentially a solved case. So what remains to show is, well, what is it? What if it is? What if your holonomy is transitive on spheres? And with that, I guess I'm gonna state another lemma. This is due to Montgomery and Samuelson, I guess. I believe. Yeah. And this was, I don't know, 1940s. So essentially, what Montgomery and Samuelson did, they gave you the list of all possible groups that are transitive on spheres. So if G is transitive on sphere, then G is one of the following. So it's either one of these infinite families. So it's either SON, UN, SUN, SPN cross SP1 over Z2, SPN cross Q1 over Z2, or SPN, or it's one of the infinite, one of the exceptional cases, which there are only 3 in this case. So it's either G2, G2 is in SO7, it acts transitively on the 7th sphere, on the 6th sphere, or it's spin 7 acts transitively on the 7th sphere, or it's actually spin 9 that acts transitively on the 15th sphere, sorry. All right, so that's quite a short and nice list. And the question is, can all of these be holonomies for some manifold, right? So actually the answer is no. So there are 2 obstructions to that. First is, if you consider this group, SPN cross U1 over Z2, Berger showed that if you apply Bianchi identities, you can actually get rid of this factor U1, and you're just gonna get SPN, which means whenever SPN cross U1 would appear as a holonomy, well, because you have Bianchi identities, you are actually secretly in just SPN. So there are no, these guys cannot be a holonomy group. And the other case that doesn't happen is spin 9. And this actually again implies that M is homogeneous. Homogeneous. It's a symmetric space. So what happens in the spin 9 case? Well, essentially, you have so much symmetry of your curvature tensor that it becomes covariantly constant, which means, again, you are on a symmetric space. And this leads to the following classification, and that's a theorem by Berger. This was in 1950s. And I'm just gonna copy the list right here.
What is covariantly constant? What does it mean? That something is covariantly constant?
Yeah, so symmetric space is the same as saying that your curvature tensor is covariantly constant. So if you show that your curvature tensor is covariantly constant, that means you are on a symmetric space. Yeah, thanks for the question. I'm gonna copy that. Right. So the list is the same, except I'm gonna erase the SPNE1 we talked about, and I'm gonna erase the spin 9 case. Right. I guess I'm gonna move you here. Okay, so these are all possible holonomic groups of simply connected, irreducible, non-symmetric Riemannian manifold. Okay, so I guess a couple remarks. One remark is that if your holonomy of a manifold is either SUN or SPN or G2 or spin 7, this actually implies that your manifold is Ricci flat. And that's quite interesting, especially if you consider the fact that we don't have any other compact examples. So let me rephrase that. The only known examples of compact Ricci flat and non-flat spaces are the manifolds that have holonomy of one of these. And we have also nice names for them. These are Calabi-Yau manifolds, hyperkähler manifolds, or G2 and spin 7 manifolds. And for some reason, we don't have any other examples of compact Ricci flat, non-flat manifolds. So I think that's quite an interesting remark. And also one more remark that I'm probably not going to write that, it's just a small remark. The torsion freeness in this case is essential. So if you don't require, Berger got this list by heavily using the torsion freeness. If you don't require torsion freeness, you can get any compact subgroup as your holonomy group. So it's really essential that you have Levi-Civita connection and not just a compatible connection, if that makes sense. Okay, hopefully that's clear. So I'm gonna focus on this talk, and I guess generally in my research, I focus on the case of G2 manifold. So maybe before I start talking about G2 structures and G2 manifolds, I want to mention, like, answer the obligatory question, why G2 manifolds? Like, what's the motivation? Why should anyone care about G2 manifolds? Well, I'm going to offer you 3 motivations for these. So the first motivation is really a big motivation for me. It's an exceptional Lie group that is exceptional holonomic group. What do I mean by that? Well, if you remember the classification of simple Lie groups, there are these 4 infinite families and 5 exceptional cases, right? G2, F4, and E6, 7, 8. And the classification of holonomic groups looks quite similar, right? We have these 5 infinite families and 2 special cases. And G2 is the only group that appears on both of these lists. So it's an exceptional Lie group that is also exceptionally holonomic group. And I mean that surely that sparks up your curiosity, like why does that happen, right? And I don't want to get deep into the woods why this is true, but essentially it has a big connection with the fact that if you look at group of automorphism of the octonions, right, you have your real numbers, complex numbers, quaternions, and then you have octonions. Well, the group of automorphisms of octonions is actually G2. And that's what's kind of driving this connection. But I'm not gonna talk about that. Okay, let's say you're not satisfied, you want another motivation. Well, another motivation is that it's actually the only odd-dimensional Ricci flat, and let's say not flat manifold, right? So that goes with the remark I mentioned earlier that if you want compact Ricci flat non-flat manifold, currently what we know so far about holonomy is that it must be one of these 4 holonomies. And of these 4 types, only G2 is odd dimensional. So let's say for some reason you require an odd dimensional Ricci flat manifold. Well, so far your G2 manifold is your only bet, right? We don't have any other examples. And I guess third motivation, which I want to mention, this is at the end, this is mathematical physics seminar. And of course, I know the least about this for motivation. So in M theory, right? You have, let's say, 4-dimensional space-time across some 7-dimensional, and you across some 7-dimensional manifold, and you wanna have M, the 7-dimensional part, to be some compactified manifold that has parallel spinor, right? So what you require in M theory, you require M to have parallel spinor. And as I mentioned in the beginning, having some parallel structure is reflected in your holonomy. So given your M is 7-dimensional, having parallel spinor is the same thing as saying M is G2 manifold. So that's one of the reasons it was like during the 2010s, I guess, quite an active area of research in physics, because physicists wanted more examples of G2 manifolds to have this 7-dimensional complement. All right. So hopefully you are all very motivated to learn about G2 manifolds. So let's jump into that. So first, let me define the group G2. I talked about it a bit. I mentioned it's an automorphic group of octonions, but it doesn't really tell you much. So first, let me define the group G2. How do we do that? Well, there are a lot of equivalent definitions, but the one I'm gonna use, which I think is like the most natural, I guess, is the following. So consider some phi, which is a free form on your 7-dimensional real vector space. All right. There's the following equation: ix phi wedge iy phi wedge phi. These i's are just interior products. Is equal to g xy d vol g. Okay. And this is just interesting fact of general free forms on 7-dimensional manifold. So on 7-dimensional real vector space. So whenever I give you a free form, via this equation, it actually gives you a symmetric 2 form and a volume form uniquely. So given this phi, there exists unique G, which is a 2 form on R7, symmetric 2 form, and D vol G, the volume form on R7. And one of three things can happen. So either your volume form is degenerate, it has like degenerate directions, so it's not actually a volume form, or it's not degenerate, and then G is also non-degenerate and has signature 70, or G is non-degenerate and has signature 3,4. And those are the only possibilities. So just let me repeat that. Maybe I didn't say that clearly. If you give me a free form on R7, via this equation, it gives me unique G and unique D volume form, such that either the volume form is degenerate or is non-degenerate, and the symmetric 2 form is positive definite, or it's indefinite with signature 3,4. And these guys in the middle, the one that give you positive definite in a product, they are called positive form. So phi is positive free form if it gives you G with signature 70. Okay, that's interesting, but what does it have to do with G2? Well, G2 is automorphism group of any positive free form. So in the same way that your automorphism group of non-degenerate positive definite in a product is always ON or conjugate to ON, G2 is automorphism group of any positive free form. So it's a stabilizer of a free form. Right? Awesome. We have a G2 structure on a vector space, and this immediately leads to the definition what's a G2 structure on a manifold, right? So we say that manifold M has G2 structure phi if there exists if phi is free form on our manifold, such that for each point on our manifold, phi at a point P is positive. Okay, does that make sense to everyone? Oh, hopefully it does. So the nice thing about manifolds with G2 structures is that they are completely classified, right? So this is a theorem of Alfred Gray. It's not in 1960s. The theorem is as follows. So a manifold M admits G2 structure if and only if M is orientable, which means the first Stiefel-Whitney class is 0, and spinable, which means the second Stiefel-Whitney class is 0. Okay. Will it make sense? Maybe just a small remark. how you should think about this relation. Again, if you're familiar with classifying spaces, you can think of it in the following picture. So M has a tangent bundle that has a metric. So the tangent bundle is classified by a map to the classifying space B07, right? And then you can ask, well, is there a lift to BS07? And this is exactly orientability. So obstruction to this lift is having first Schiffer-Whitney class equal to 0. Then you can ask, well, can I lift it even further to BAS spin 7, right? And again, that's the same as having spinable manifold. And obstruction to this is a second Schiffer-Whitney class equal to 0. And you can ask, well, okay, can I lift it into G2? And the point of this theorem is that this lift always exists. There is no extra obstruction. Once you are in spin 7, you can go to G2, right? So one of these implications is, this implication is trivial, and the other implication is that's the theorem. Okay, so those are manifold with a G2 structure. Are there any questions to that?
What do you mean that the M admits G2 structure? It means that the tangent bundle admits G2 structure, or the
Yeah, exactly. We mean that the tangent bundle admits a reduction of the structure group from 07 to G2. Yes.
And it might be also a subgroup of G2, or it must be the whole G2.
It can, yeah. So for this definition, it can be a subgroup of G2. Right. So with this definition, tori admit G2 structure.
Sphere. CP1.
And we'll also wonder about one thing.
Yeah, and also they are 7-dimensional. Yes, of course.
Yeah, 7-dimensional. Okay.
I guess I should write it down. We require M to be 7-dimensional.
Okay, I have a question. Does it matter whether this three form is closed or?
No, there's no other condition on the free form other than it must be positive, and the positiveness on itself doesn't imply closeness or anything.
And if it is closed, is it somehow nicer, or is it just?
Yeah. We're gonna get to that, but yeah, if the form is closed, the structure is much more well behaved.
Okay.
Yeah. Thanks for the questions. All right. So if there are no further questions, let's get to the G2 manifold. Right. So definition, you say that M is G2 manifold if and only if the holonomic group is inside G2, right? That's not surprising. Just gonna make it clear. But it was actually shown by, I believe, Bryant in 80s that if you have a G2 structure phi, so maybe let phi be a G2 structure, then he showed that if phi is closed and phi is co-closed, this implies M is G2 manifold, right? So essentially the problem reduces to finding a metric with a nice holonomy, reduces to the fact of finding a nice G2 structure, and by nice we mean closed and co-closed. Okay, that seems very simple. The problem is with this codifferential delta here, because as you know, codifferential depends on some metric. So what is this metric? Well, the metric is the one given by phi. So if you remember, we had this equation, which is highly nonlinear. If I give you phi, there exists unique G, the metric that satisfies this equation. So every G2 structure gives you a Riemannian metric. And of course, like this, maybe just a remark right here, that's not surprising because G2 is a subgroup of SO7. So having a G2 structure is even better than having SO7 structure, and SO7 structure gives you metric and an orientation. So it's not surprising that you're getting metric and orientation from a G2 structure. But what's the consequence of that is that this codifferential depends on your metric in a highly nonlinear way. So this is not some easy first order ODE that you can solve because it's highly nonlinear and it's actually not easy to solve. And that's the whole business with G2 manifolds, let's say. All right. So that's nice. Now we know what we need to solve. And there's a small observation that on a compact manifold, right, these two conditions can be summed up by saying that a Laplace of phi is equal to 0, right? This is equivalent to saying phi is closed and co-closed. But again, it's co-closed with respect to the induced metric, which means this Laplace is with respect to the induced metric as well, which turns this guy into non-elliptic, nonlinear second order ODE. Okay.
ODE or PDE?
PDE, sorry.
Okay.
If I said ODE, sorry, that was a misspoke. PDE, of course. Right. So, first remark, there are solutions. And this was shown by Dominic Joyce in late 1990s. And he showed that there are compact examples of G2 manifolds, which, as we now know, is equivalent to saying that they are harmonic free forms, but harmonic with respect to the induced metric. And later, it was shown by Kovalev, I believe in 2010s, early 2010s. There's actually another technique for constructing compact G2 manifolds that involved essentially taking two Calabi-Yau free folds, multiplying them by circle and joining them, like doing a connected sum, but with some twisting. I don't want to get into the details, but it was another construction. And I believe that these two are the only constructions known to date, like only two known constructions for constructing G2 manifolds, compact G2 manifolds. Another remark, people studied flow for this equation. So by that, we just mean a family of free forms such that they evolve via this equation. And there are some nice results that give you convergence and actually parabolicity even if you require that your free form is closed beforehand. So essentially you're assuming half of your equations and then you can solve the nonlinear part quite nicely, essentially. And this was done, for example, by Jason Wattey. That's 2020s. Okay. And what we're going to look at is Poisson equation for this operator, right? And this may seem like weird. Why would we look at Poisson equation when we don't understand the Laplace equation? Because, like, remark, this is more general. But it has one big advantage, and the advantage is that for every manifold M with G2 structure, there exists a solution, right? Which is obvious. We're just gonna plug the free form in, the Laplace is gonna do something, and we're gonna end up with some free form. So this might seem like a trivial remark, but this is actually very nice, because this means that we can study this equation on any manifold with just G2 structure. And as I mentioned before, these are classified. So we have like this big playground where we can study this equation, and we don't have to solve this harder problem of finding the kernel. We can understand the operator in a much bigger space. In particular, we can understand this operator on homogeneous cases, a homogeneous manifold G over H. So maybe I'm just gonna say this, but for a homogeneous manifold, there are no interesting solutions to this guy, right? Why? Well, if I give you a homogeneous manifold, and let's say you manage to solve this equation, which means you have compact manifold, which is a G2 manifold. Well, but that then, by a remark I mentioned before, you have a Ricci flat homogeneous space, but Ricci flat homogeneous manifolds are actually flat. So you are on a tori, and it's not an interesting solution. You are actually flat. Your curvature is 0. There's nothing to do, essentially. It's right. But for a Poisson equation, there may be some interesting solution for a Poisson equation, and homogeneous manifolds are much easier to work with than general manifolds, and you can try to solve your Poisson equation there and maybe understand something about the operator. And in fact, that's exactly what we have done in our project. I'm gonna get to in a second. I just want to state first a theorem by Wadsworth and Polomotov, which are actually my advisors, in 2024. It's quite recent. And they have shown that for every nu that is positive and closed, there exists locally phi is also positive, such that it solves the Poisson equation. Mind you, this is only local result, but you know that it works for any positive and closed right-hand side, right? So now the question becomes, what about global solutions? Right? And that's exactly what we have done. And we have used the fact I mentioned earlier, and we can work on a homogeneous manifold. And the main advantage of working in a homogeneous manifold is the following isomorphism. That is that if I give you a free form on a homogeneous manifold, that's G invariant, right? So I'm assuming a lot of symmetries. This is in bijection with free forms on the factors of the algebra. That's H equivalent. But this guy on the right-hand side is finite dimensional. So essentially, by working on assuming a lot of symmetries, enables you to reduce your problem to a finite dimensional problem, which is amazing, right? Okay. So pick your favorite 7-dimensional homogeneous manifold, and we can start. So what we have done, we have chosen the 7th sphere, which is, I guess, obvious choice. So the 7th sphere. Okay. So the first thing we need to do is we need to decide what are the possible homogeneous structures on S7, right? How can I write S7 as G over H, essentially? Well, for that, I would need to have all groups that act transitively on a sphere. hang on, I have a lemma for that. Right, somewhere here. I have a lemma about all the groups that act transitively on a sphere. So I know it can be, so it is enough to have, to choose the groups that have the right dimension, which are, of course, all of these infinite guys, plus the spin 7. And those are all homogeneous structures on seven-dimensional sphere. So let me just write it down real quick. So it can be either SO8 over SO7, is actually a symmetric space. It can be U4 over U3. It can be SU4 over SU3. It can be the exceptional case, spin 7 over G2. And then it can be all of the SPs. So that's SP2 dot SP1 over SP1, SP1. This dot just means the usual product of groups modulo Z2, but that would be too many Z2s, which I don't want to get overwhelmed. SP2 U1 over SP1 U1. And the last one is SP2 over SP1. Okay, so these are all the possible homogeneous spheres. Mind you, there are quite a few. Is actually the sphere with the most homogeneous structures there is. So let's start with this. Let's start. So first thing, there are no G2 structures on SO8 over SO7 and U4 over U3. Well, why is that? Well, because SO7 and U3 are actually not subgroups of G2. So they don't stabilize any free form. So there are no G2 structures, so there's nothing to do. So this doesn't work and this doesn't work. Okay. Interestingly, for the next 3 cases, you actually managed to compute the Poisson equation and solved it, actually. So the following theorem. Let G be either SU4, U4, or SP2 dot SP1. Then what we have shown that for every nu, which is a free form on S7, such that nu is G invariant and positive, there exists unique free-form phi on S7 such that phi is also G invariant and also positive and solves the Poisson equation, right? And I think that's quite a nice result because it tells you that the operator, this weird nonlinear operator, is surjective on positive forms. It doesn't have image anywhere else, and it's injective on positive forms. So essentially everything you can wish for is injective, surjective, and it maps positive to positive forms. So this seems like this operator is going to be very nice and everything's going to work, right? Well, no. If you consider, maybe I'm just going to put a little tick here. Right? So if we consider the other case, SP2 times U1 over SP1 U1. So, sorry. We consider this homogeneous space over SP1 U1. What actually happens is you get 4 equations with 4 variables. It doesn't seem that bad. But the degrees, yeah, it's you're gonna get, I didn't mention that, but you're gonna get that the Laplacian is just a set of rational functions, but the degrees are from, I believe, -4 to 7. So you have 4 equations with 4 variables that are, each equation is a rational functions where degrees range from -4 to 7. In other words, it's a mess, and it's really intractable, right? So it's. But what we have done is we noticed that this G2 Laplacian has nice scaling property. What does this mean? I'm just gonna write it down. So if you put there C phi, you actually get C to the 1/3 phi. So it's not exactly linear, but it's in some way homogeneous, i.e. it preserves line and behaves nice to scaling, which means we can kind of reduce this 4 to 3. And nice things with complicated equations in 3 variables is you can visualize them using some numerics, and that's exactly what we have done. So we just took cube of points in this new 3-dimensional space. We plugged it into our operator, and we looked at the results. Like try to, like, maybe it's gonna look very nice and we just cannot solve it, or maybe it's gonna be horrible, but it's gonna give us some additional information, right? How does the operator actually looks? So we did the numerical simulation, and what we have done, what we got away were these pictures. Okay, maybe I erase that. So first of all of these guys are positive, and all of these guys are not positive. So essentially, immediately one of our conjectures goes out of the window. It doesn't preserve positive forms in general. Furthermore, even when we were scaling our cube up, so we were just plotting more and more points, this region seems to be empty all the time. So it's most likely not going to be surjective, but that's just an evidence, not a proof. But what's worse, if you zoom in on this tail, you're going to get this picture, and it's clear that it's not injective either. So that means that all of our properties don't hold, they just break. So for this case, it's not injective. It does not preserve positive forms, and probably, in quotations, not surjective. We're working on this, but most likely it's not. So yeah, everything kind of breaks. It's not a very nice operator. And yeah, so if you're asking, maybe I'm gonna put like half tick here. And if you're asking, well, what about this space? Well, it's only gonna get worse. So what you will end up with are 10 equations with 10 variables, and you're gonna get the same degrees. So it's gonna be again from -4 to 7, and there's not really any chance where you're gonna get any of the nice properties back. So it's gonna be probably like the even bigger mess. Right. So yeah, that's essentially what I wanted to say today.
Thank you very much, Štěpán, for a nice exposition. And, now, if we are not too sleepy, we might have some questions.
Sure, go for it.
Please ask. So maybe I'll start with a kind of silly question. You told us that you can reconstruct Gn volume form out of your free form.
Yeah.
How does this work in opposite direction?
Sorry, come again.
If you start with your G and volume form, what's your freedom in choice of your
Oh, right. Yeah. So there's actually quite big freedom. So maybe I can.
It's anyhow interesting freedom.
Yeah, it's actually very interesting. So you essentially you're looking at this homogeneous space. This homogeneous space tell you all the G2 forms that give you the same metric and same volume form. And this homogeneous space is actually isomorphic to RP7.
I see.
So this gives you a lot of freedom if you're on a manifold, because imagine you're on a Riemann manifold with orientation and you're looking for a G2 structure that gives you this Riemann metric and volume form. You're essentially looking for sections of a bundle where typical fiber is RP7. Right. So once you have at least one section, there's a lot of choice.
Okay. So there is apparently one question from chat. Vít is asking, could you please repeat what equations are solving in the end? It's more specifically speaking delta.
Yeah, we are solving the Poisson equation for
yes, most likely
right hand side.
For a symmetric.
Yeah. So you are on S7 and you represent S7 as a homogeneous space.
Yes.
One of these three guys. And given the positive free form, it gives you a metric and an orientation. The metric and an orientation gives you the Hodge Laplacian, and that gives you this whole operator. And you're essentially solving like for any mu on right hand side. And it turns out that you have solution and it's unique if and only if the right hand side is the same level of invariance as your 5, and it's also positive. Does that answer the question?
Štěpán?
Yeah.
Do you have any idea whether this has some meaning now in this theory compactification?
Sorry, come again. I didn't hear you clearly.
Whether this has some interpretation for this M theory compactification. Or not. I don't know. Whether this kind of equation, solutions of this equation can tell you something about it. Yeah. Something interesting for M theory.
Yeah. Whether it's part implications in M theory more directly.
I don't know. Sorry, I don't know much about M theory, so I have no idea how does this right. Like all I can tell you is, I think Fritza told me that you require you get a condition on essentially parallel spinor, which is the same as requiring, like parallel spinor is the same as essentially having this integrable spin 7 structure, which is the same as having the G2 structure, integrable, which is exactly why it transfers to having a G2 manifold. But sorry, I don't know any physics that would like implication to physics or so.
Okay, any other question? So it doesn't seem to be the case. Let me speak. Let me thank the speaker again, please.
Okay.
Štěpán, for your nice